Thanks for being here early in the morning. I'm going to give you a little bit of music. I'm going to assume that most people here have seen spectrograms before. Maybe at about, a few hundred samples hop length, for those who know what it means. That is not my music. Can we have that? Yes, thank you. So this is down to 32 samples hop length. So usually you don't see this at this speed. And what I want to show you is that you don't need a huge computer to do that, and it's actually real time with very low
Live from London,
latency.
This is BBC News.
So that's what I'm going to show you today, how I did that. This is online on YouTube, so you can go watch everything. You can see a lot of details and so on. I was an academic a while ago, and this research is rooted in my academic. This project is rooted in my academic research. What I've always been interested in is interactive systems that involve brains. My background is not in electrical engineering, which might be why I look at things a bit differently. And that's how I came to this. So I've been lucky enough to, at the time, do some work on some interesting fun projects, like real-time analysis of tonal context and visualization and improvisation systems. At the time, we were doing MIDI because, that was like 15, 20 years ago. We needed bigger computers and so on. These days, we can do the same thing with a phone, or better with a phone. And in fact, at the time when I revisited this as a hobby, to do it on a phone, it was easier to take the audio and do an FFT than to figure out how the MIDI libraries had evolved. That has changed. Now MIDI is in there, so that app is on the app store, and it works, but not great. So the question that I want to answer really is, which frequencies of interest are present in the input signal, right? That's what MIDI was giving us as a shortcut. In this day and age, or for the past, 70 years, the answer seems to be the FFT. But is the FFT really the best solution in all cases? Spoiler alert, maybe not. It comes with, it's the FFT, so it's great, it's fast, it's wonderful, it gives you your discrete Fourier transform really, really quickly. But for this particular applications, it doesn't give you what you want in the first place. It gives you linear frequency bins. It introduces some delay that is at the limit of what you want to have for an interactive application with bigger and bigger and faster computers, but still at the limit. And there's a whole bunch of things you need to do afterwards that make it not that fast in the end. So I propose a different approach. There's an actual paper, a more theoretical paper in ICMC. It's online. It's based on a simple resonator model, very cheap, very easy to implement iteratively, no buffering. That's one of my mantras. It's analogous to a bank of nonlinear filters. It's probably at least similar, related, maybe identical to some existing algorithms, but I've never seen it actually used. The main disclaimer is this is not a better FFT. If you know you need the FFT for some reason, and there's many good reasons to use an FFT or to compute a discrete Fourier transform in many applications, do that. This is not a better way to do it. This is a way to get to answer my question. Which frequencies of interest are in the signal? It has all the reverse properties that I highlighted as bad properties of the FFT. It seems to be giving reasonable results, and it's easy to implement. So in this talk, I'm going to share more of the intuitions behind some of the things that are important or that I think are important, and a bit of code. All my code for this implementation is released in open source. But this has been a weekend and holidays and breaks project. So I'm putting it out there. It's all under MIT license. If you're interested, look at it, see what you think about it. It's not perfect code, it's proof of concept. And in the Git repositories, there's the whole history of all the dumb things I did on the way there, but that's how you learn, right? Yeah, let's see where we go. So there's an app, the one I just showed you on the iPad. It's free. You can download it. Sorry, it runs only on Apple platforms because that's what I know, that's what I have. But that's a start, I guess. All right, let's get into it. So I will show you how the model and implementation for a single resonator, then how to assemble those resonators into banks, and then some applications. If you paid attention yesterday at the quiz, this is a cosine, right? It's even. So what's a resonator? A resonator is a device or system that exhibits resonance, meaning it oscillates with greater amplitude at certain frequencies than others. So let's take a very simple example. You have an oscillator at a given frequency. That's the top. Yes, I have a pointer. That's the top one. You have an input signal, let's say also a sine wave or a sinusoid of also amplitude 1 to keep it simple. And you multiply the input signal at each sample by the value of the oscillator at each sample. And you get something like this if they have same frequency and the peaks are aligned. You can see intuitively that's when you'll have maximum response. If you have, if they're not aligned, well, you get something a bit more erratic. And if you take the average over a certain amount of time, they will cancel out. Right, so the average here is around 0. The average here is maximal around 0.5. I don't have time to go into why it's 0.5, but that's the way it works. So now, if they're not exactly aligned, which is the middle column here, they're still same frequency, but not quite aligned. You see that the response is lower. You still have a higher response than 0, but it's lower. But remember, we want to know how much of each frequency is in the signal. So what we're really looking for is the amplitude of the input signal. Now, if the amplitude of the input signal is not 1, it changes, you also get a lower response. So there's two things we need to recover. So in math terms, the phase and the amplitude. The phase is the offset. In math terms, that means there's 2 degrees of freedom, so we need to get 2 measurements per input signal, per input sample. And we're going to use cosine and sine, because again, if you paid attention at the quiz yesterday, this is Pythagorean theorem. The cosine square plus the sine square is always equals to 1 in this case. So we're going to multiply our input signal value sample with the cosine and with the sine. There, the other important thing is that the cosine and the sine are offset by 90 degrees, if there's the same frequency. And this way we get 2 measurements, and using those the Pythagorean theorem, we can recover the power or the amplitude of the input signal, and we can also recover the phase using the arctangent. Very conveniently, so this is just the intuition behind it. To link that to maybe more conventional way to think about it, the sine and cosine of same frequency and same amplitude, you can write that down as a complex number. Right, so either we do where the cosine is the real value and the sine is the imaginary value. So it all comes back together. You can use it either independently or as a complex number if it's more convenient. And there's no magic here. This is actually, sorry, I'm going back. This is actually exactly what's going on in the FFT. Okay, we're just going to use it a bit differently. So first thing, we're going to multiply our input signal with a sine and a cosine. We don't want to call a sine function or cosine function at every sample, or even do that. So there's different ways to do that. Maybe in the audio community, wavetables are popular, where you pre-compute a lookup table and then do interpolation. For this case, I'm really interested in an iterative implementation rather. And so I discovered a bit more recently the concept of a phasor, which is apparently a classical thing in electrical engineering. So a phasor, for convenience, it's formulated as a complex number, and you can think about it as having a complex number, a vector of magnitude 1 with the origin at the origin, and it's on a point on, well, it's pointing to a point on the unit circle, and you can think of the phasor as increasingly rotating. And this rotation is written as a multiplication, a complex multiplication. The amount to rotate for each input sample is dependent on the frequency. So that's the equation that's up here. You want to do a full circle at your given frequency. You want to know by how much you need to rotate for each input sample. You can pre-compute a lot of it, and you can express this complex multiplication with just 3 real multiplications. Anyways, the point is, it's very efficient, very cheap to compute at each input sample. Now, because this is real life, and the thing that you don't see in the mathematical equations is that you accumulate error, right? Approximations. So every once in a while, you need to renormalize the vector. And again, there's a very efficient way to do that. I will maybe not spend any time on this, but that's how it works. Now, the question is, how often do you need to do that? I don't know. The short answer is that it's so cheap and so fast anyways, you just do it as much as you need. It might be more expensive to figure out whether you need to do it or not than just doing it. At least for my demo and for my proof of concept. Of course, if you want to do something hyper-optimized, you need to consider this question. Right, I think that's how much I want to show about that. The next thing is, you remember we need to average over time. The FFT averages over a buffer, so you need to buffer. That introduces latency. What if we don't want to buffer and have no latency? There's this wonderful thing called the exponentially weighted moving average. Again, some classical data analysis methods. I'm not inventing anything there, just using things a bit differently. In electrical engineering, it's known as a low-pass filter. So the concept behind it is extremely simple. You have you're measuring samples. Yes, this is it. You are measuring input samples of something you're trying to model. You want to remove the noise in it, your measurement noise. So at every step, you're going to take whatever you thought it was, this part, and move it towards what you measured, right? So this alpha is between 0 and 1. If alpha is 0, your model is never going to change. You start with an estimate, and then you never update it. That's not very useful. If alpha is 1, each new sample becomes your estimate. That's not going to remove any noise. So somewhere in between, there's a sweet spot where you smooth out the noise, and you keep that. What does it mean for us? You're computing basically a moving average without buffering, where the weight of each measurement decreases exponentially in time. So your latest measurement has a higher weight than the older ones, and it goes down. And that's pretty much what we do from that makes sense from a perceptual point of view, right? More than having a buffer with a window and some magic in it to make it work. So this is very simple, very cheap to compute. There's one single parameter that can be related to a time constant. And we'll see how that works out later for frequencies. Right, so how do we do our resonator? Remember, so we are multiplying the input sample by the cosine and by the sine. We maintain a cosine and a sine wave, and we multiply each input sample by the value at that time. We are taking our exponentially weighted moving average of it, so that's the whole alpha and 1 minus alpha. C and S are the smoothed out values, and those are the ones that we're going to use to infer the volume, the amplitude and the phase of the input signal. It can be, okay, any decent compiler, at least high-level compiler, will do something like this for you. You don't have to do it explicitly, but this is going to come in handy to think about a bit later. So I'm just putting it there. Pre-compute everything you can. So if we do that, we've seen already, I've mentioned the complex phasor iteration. If you look at the signal, so this graph here shows the value of the power, because who needs to compute a square root when you don't have to? The power over time when the system starts from 0 and is subject to an input, a step function input to 1. And you can see that it converges towards some value. Because it's the power, it's 0.25, that's 0.5 square. But you can see that it still oscillates, and there's good reasons for that. It's still an oscillating function. So we add one more step of smoothing to remove those oscillations, because you get a bit dizzy if you look at it too long. So, of course, we know how to do that with our exponentially weighted moving average. So that just adds one more step, very cheap to compute as well, and very low latency as well. And then you see that you remove the oscillations. Okay, so that's great. That's how we do one resonator. So there's one parameter. It's set heuristically. That's a polite way to say you just make it up. So how do you, well, you can't just make it up. You have to look at what makes sense, maybe, if that makes sense. So I said you can relate that to a time constant. And since we're dealing with audio and frequencies, intuitively, if you have short frequencies, you don't need a very long time constant to converge towards what you want. If you have lower frequencies, longer waves, you need to look at it for longer before you can be sure that you're looking at the right thing. So, the time constant should be inversely proportional to the frequency. Then you look at it long enough, you throw in a log of 1 plus the frequency at the top, because why not? And then you add a constant just to tweak a bit if needed. For the applications I'm showing, I just use one. Well, since I'm giving tips, if you're looking at lower frequencies, it probably works better with a higher K, like 3, 4, 5. But you have to try it and see what works and what doesn't. That's heuristics. Anyway, so one single parameter per resonator. What does this do? It tweaks the dynamics and it tweaks the response range. So here's a few graphs from the paper. I've talked about the top ones already. So this is showing 100 hertz input, 1,000 hertz input, and 10,000 hertz input on resonators tweaked with the heuristic. If you don't smooth, you get oscillations. So you smooth out to remove the oscillations. Lower frequencies takes longer to converge. Higher frequencies converges really, really, really quickly. And this is the response for different input frequencies at steady state. Again, a step function at steady, once you reach steady state. And you can see that the response is centered on the resonant frequency, which is what we want. It's not too wide and not too narrow. it looks well behaved. Again, heuristics, you need to tweak it to make it work to your own purpose, probably. Although what I showed you is just the default that I did. It's very cheap. 6 floats to maintain our 3 complex numbers with the smoothing. Just a handful of multiplications and additions. There's a bit of overhead sometimes, so cheap as well that you don't even have to worry whether you need to do it or not, just do it in some cases. The complexity is constant, that's very important, per sample. And so it grows linearly with the number of samples processed. Some fun applications that I can mention that. So just with one resonator of given frequency, if you know the resonant frequency, and you have an input sinusoid of given frequency, if it's the same frequency, you will get maximum response and the phase will be constant. They will be in phase. It doesn't move. If it's not exactly the same frequency, it will just be a little bit faster and you will see your phase drift. So in this case, it's a little bit slower. So the phase drift. From the phase drift, you can recover the actual frequency of the input signal. And that's what's shown here. That's in the app as well. That's a screenshot from the app. So you can recover. This is the input frequency. This is the resonant frequency, and you can see that you can recover the actual input frequency. Now, if you know it's the same frequency, but you do not measure the same frequency, you can do a Doppler velocity computation and figure out how fast and in which direction the source is moving with respect to the microphone. I have a YouTube video on that. That's fun. Anyways, so there's another application which is a stereo directional estimation from stereo phase difference. That is not in the app because I don't have the equipment to actually test it. But I've played with that. If you're interested and have the right equipment, talk to me. I would love to see it work. So that's how we make one single resonator. But of course, there's more to life than just one frequency. So we can assemble those resonators into banks. And here we can have an arbitrary number, no need for powers of 2. We can tune them independently any way we want, any frequency we want. So maybe a log scale frequency that makes sense, between maybe 32.7 hertz and 10,000, 20,000 hertz. It doesn't really matter. We can distribute them any way we want, maybe on a scale, or a male scale, or anything we want, and we can tune the dynamics independently. That also means they're all independent, so we can do the computations in parallel. And again, that's analogous to a bank of nonlinear bandpass filters, which is not new. But why didn't people do that with music? I don't know. Or maybe they did and I don't know about it. So if you know, let me know. So how do we do that? So there's 2 main directions. The first one I took was the simple one, which is you have implementations of resonators. You put a bunch in an array, and then you call the update function for all of them for each input sample. That's very simple. That's I forgot to mention, this is not running code. It's a mangled version of the Swift code in the repository. If you want running code, go to the repositories. Otherwise, this is just redacted for legibility and simplicity. So you just do an array of the resonator objects and do that. And that kind of works. Actually, it works really well as a proof of concept. But there's a better way to do that, or a more interesting way is to vectorize the whole thing and use SIMD acceleration, because, again, parallel. And one of the nice things of the FFT is that it's hardware accelerated on many devices, but the same tools used to accelerate the FFT are the ones we're using here. So we have the power to do all that. Let's look a bit at what that looks like. So remember, on the right, here's the single resonator example. And remember, I said you probably don't need to do that explicitly for a single resonator, but it's convenient to think about it this way, because when we vectorize, we're going to do pretty much the same exact thing on a vector. So there's a few things to remember here. This is from the Swift version. Swift arrays are great, but they have a huge amount of overhead to make sure you don't do anything stupid. The overhead, when you do it 44.1 thousand times per second, becomes a bit of an overkill, because if you don't do something stupid the first time, it's probably not going to be stupid after that for the rest of it. So anyway, so in C++, there's no such question. You have to manage your memory. In Swift, you have to use unsafe pointers, which is very scary, maybe, from the name. But yes, just you do it once and then you're good. So we do pretty much the same thing. Those are very simple SIMD accelerated functions. This is a vector scalar multiply. So we pre-compute this term. We have pre-computed at initialization the 1 minus alpha. Those are all vectors now. And we just do this simple exponentially weighted moving average computation, which is a vector multiply multiply add. So we multiply the vector on the left, multiply the vectors on the right, add up, one call. Then we do the same thing again for the smoothing, and we're done. So very cheap, very fast, very efficient. So there's a few other things we need to advance the phaser. For this, it's more convenient to think about it as complex numbers, because there's a function that does exactly what we want, the complex multiplication. So we use that, and the renormalization of just use standard functions. There's a reciprocal square root function, which is very optimized, convenient, cheap. Again, you don't need to decide whether it's worth doing or not, just do it every once in a while, and it works. One thing to see here that I find interesting, or that I want to point out, is that those vectors are of size 2 times the number of resonators, because they're floating point numbers, and each you need to keep track of the cosine and the sine, or the real part and the imaginary part of the complex. So sometimes it's easier to consider the numbers as vectors of twice the size, of float vectors of twice the size, which is why it's 2 times. Sometimes it's you just map that to a split complex and you use a complex function to manipulate it, but it's the same thing. All right, so funny thing, I realized yesterday I did those screenshots on a debug version running in Xcode. So the numbers are not quite exactly what I intended to show, except a couple of things. So because it's a debug version, the overhead on the Swift implementation is important. So these are not the best the best numbers you're going to get on the Swift implementation. The app lets you switch between the different implementations and shows you the processing time per sample, which is these screenshots. So the Swift line will have more overhead compared to the actual release mode performance. The C++ not so much, because the debugger doesn't know about C++, I think. So it doesn't make a huge impact. All right, so what's on the left here is the sequential updates on the array of independent resonators, so non-vectorized. So this is the worst number. And it's a debug version. And the processing time per sample is less than 20,000 nanoseconds. So to put things in perspective, one sample duration at 44.1 kilohertz or 48 kilohertz is in the order of 20 microseconds. So this is still less than the sample time. The computation time is still less than the sample time. In Swift, in debug mode with sequential update. Okay. Not surprisingly, the C++ implementation is much faster. This is about 1,000 nanoseconds. Now, if you do concurrent, I tried a few things with concurrency to try and see what we can get. Because of the overhead of the memory management and other things, you get a huge reduction, even in debug mode, in processing time in the Swift implementation. In C++, it takes more time. So there's two possible reasons here. One is I did something very stupid, and I didn't go back and correct it, or I didn't pay attention, which is a possibility. Or it's just not worth setting up concurrent, threading, because it's so fast already. You spend more time trying to organize things and when to consolidate the result. I don't know, and I didn't have time to go back. It doesn't matter because I'm not really using that version anymore, because look at that. If you do the vectorized implementation, you get in the order of 100 nanoseconds processing time per sample. And that's the same on a phone, the same on an old iPad, and so on. So it's very, very efficient. I'll just say one thing about the Swift one. It's actually much closer in the release version to the C++ version because they call the same accelerated functions anyway. So and with using unsafe pointers, there's no overhead. These are the things that go without saying, but like one of my math teachers used to say, goes even better with saying it. There's a bunch of things you don't want to do at every sample. You don't want to do any allocation. You don't want to copy or duplicate data. Although most accelerate functions can operate in place, the ones I show you, I think, have no issues. But there's a few that do not, and I got bitten by that a few times. So be aware of that. You don't want to perform any unnecessary computations. Pre-compute everything that can be pre-computed. And you certainly don't want to leak memory at any time, of course, but especially at 48K. But if you do, you'll find out really quickly. So it's easy to. All right, how am I doing? Wow, I'm actually going faster than I thought. All right, so some applications. The app I showed you is available. It's free. It's a playground. The code is not open source, not because it has anything revolutionary in it, but because I don't have time to make it pretty enough. And I want to be able to just do whatever I want. By the way, if you download it or if you've downloaded it before, make sure you get the latest version because the latest iOS, I hope it's the latest iOS updates, broke something that was giving the wrong results in the spectrograms. So I had to do an emergency release Sunday. So hopefully I fixed most of it, but there's no guarantee. But it works well enough for what I showed you. So what I showed you is correct, so it should work properly on iOS 18. And on laptops and Macs. So it's a playground. It has different demonstrations for single resonator, just spectral analysis, and spectrograms, chromograms, MFCCs, if anybody knows how to read MFCCs by sight. But anyway, so it's fun to try and revisit those classical audio features, but do it in real time at a hop length of 32 or better. You can get a measurement at every single sample. Whether you want to do that or not, certainly not for display, but that's an option. The app is written with AudioKit to get the, so shout out to AudioKit because it made my life so much simpler. For the input, I make some taps that are similar to an FFT tap, for example. So it's quite simple to integrate these libraries into an app like this. It's using SwiftUI for the rendering. Again, it works well enough for a demo. It might not be the most efficient thing to do for if you're graphics heavy or if you want to do something a bit more elaborate. It uses the Resonate Swift package. If you click or tap on the little settings icon up there, you get the settings pop-up that I screenshotted earlier with the statistics. You can change a few things. I would not recommend changing the actual buffer length because that's a bit iffy. The default is 32 samples. So that means for display purposes, you can go down to 32 samples hop length. Yeah, I think that's, there's some YouTube videos demonstrating a bunch of things that I invite you to go and look at. So what other applications? So the one that I really wanted to have ready and to be able to show you would have been the MuseArt one, which does tonal analysis and visualization in 3D, in a 3D model. That's beautiful, that I did as a collaboration, the first one like 25 years ago. Very different kind of experience at the time. But now I'm very close, but there's only so many weekends and not quite there yet. But the input to that would be based on the chromogram from the Resonate output, because that gives you pitch classes, and then you can apply the tonality model to get the actual tonal analysis. I played a bit with Juice plugin. Just to see how hard it was, because I'm not an audio developer. It was fairly easy to just put in the C++ implementation in the Spectrogram FFT demonstration, the demonstration tutorial project. Took me less than a weekend, so it can't be that hard. But I had to leave it there because, again, only so many weekends. But it's definitely usable. The problem is my C++ implementation uses the Accelerate framework, which is Apple specific. Maybe a more optimized implementation using something more portable like the Eigen library would be useful. Again, I don't have time to do that. So if you're interested and want to do that, please go for it and share back with the community. And then, of course, I cannot just stop without mentioning machine learning a bit. So it won't solve all your problems. It might save some memory and some computation. It will definitely make inference much faster if you replace the constant Q transform, for example, as an input, or whatever you're using for tokenization. It can accelerate, at least for inference. But yeah. So I have another project that is also open source that's called NoFFT. That's a Python wrapper around pretty much the same C++ implementation. Basically because I needed that to make figures for the papers and so on. But again, it's very. I'm not a specialist in Python or anything like that, so it needs help. If you want to help or if you're interested, you can start from that. Again, it would be nice to share back, but it's all under MIT license, so you can take it and run with it. Another question is it worth doing a GPU implementation? For me personally, no. But for people doing a lot of computation, maybe for training, that might be useful. But remember, it's an autoregressive algorithm, an iterative algorithm. You cannot vectorize across time. You need to compute slice by slice. So if you have many samples in one slice, maybe it's worth doing. It's probably worth doing. Otherwise, for real-time implementation, CMD on CPU is just fine. All right, I think that's it. I'm going to stop here. Thank you.